or something. But this is all about the US election, and given it's 1 week away, at least it's current and it's somewhat pertinent. So I'll hopefully keep your attention for a little bit anyway. Right, so let's have a look at what we're doing. So let me just set the scene first of all. And this is a very, very general set of statements. The goal of research, and I think this applies to every type of research, is to uncover something new about why things are the way they are. That's what it's all about. We're trying to discover how our world works, basically. And we're often prompted to ask this question by observing data about things, right? Whatever those things are, and we all have different things that we're working on in different disciplines. And we notice that the data on these things vary over time or over space or both. And that prompts us to ask the question, why? Why is that happening? And basically, what we really want to know is, how did these observations arise? Or what processes generated these data? How did these data come about? Or just more basically, why are the values of whatever things we're looking at sometimes high and sometimes low? So this is how we all kind of start and being stimulated into doing some research. And classic things, okay, we look at maps of distributions of data in our realm anyway, okay? So we look at maps like this, and this is, there are millions of these kind of maps. This is stroke related to death rates by county across the United States. And the denser purple areas are those with raised levels of stroke-related deaths, about 3 times higher than the lighter areas. So we see this shading. The first thing we notice is that it's not random. It's not a random pattern of degrees of purple on this map. There are clearly concentrations where stroke-related deaths seem to be much higher than in other areas. Okay, and we see that immediately. We pick out the kind of deep south, Florida, as it often is, central and southern Florida as an exception to the south. The northeast being light, Arizona, New Mexico being very light. A divide down Texas, and we see it rising again in the northwest. So we immediately start thinking, why? What's caused that? Same thing with how Britain voted in the Brexit referendum, which now seems a million years ago, but we're still dealing with it. Again, we look at the map of how various constituencies voted. The blues are areas that the majority of people voted to remain within the EU. The red areas are those where the majority of people voted to leave. And again, the first thing we notice when we look at this map is it's not random. Right? All of the 74 Scottish areas voted to remain in the EU. Most of the English ones, for example, voted to leave. And even when we look at things like Northern Ireland, it's split geographically. Right? The more Protestant areas voted to leave, and the more Catholic areas voted to remain. And in London, again, we see an equally non-random division. Central and West London typically voted to remain. Eastern parts voted to leave. So again, we automatically think, well, why? What's caused that? It's not a random set of events or processes which have led to this outcome. There must be something else behind it. And then finally, the one I'm going to be talking about in most of my talk today, the 2016 presidential election. This is how we voted in the United States by county, mainland, continental United States. I've not got Alaska and Hawaii on here. So this is how we voted. The red areas are where these are percentages of people who voted for the Democratic Party in a straight fight between Democrats and Republicans. So basically, the red areas are those which a majority of people voted Republican, and the blue counties of varying hues of blue are those where the majority voted for the Democratic Party. That obviously gives you a misleading impression because it's an area-based map. It's that thing here. If we do it by population-based, we see the net result being the country is almost 50-50. It's an even split between Republicans and Democrats. But what we're looking at here is clearly, again, not a random pattern. It's not a random scattering of blues and reds. We see big concentrations of reds and to some extent, concentrations of blues. Okay. So again, the question is why? What what are the factors which cause this bifurcation in how people see our political parties? Right, so what is it we do then when we look at these maps of data and we start to analyze them? Well, we've got these data out there, and the first thing, the only thing we can do really, is to measure some associations within the data. We see what links with what seems to correlate with what seems to move in the same direction as other variables. So we try to measure these kind of spatial associations in our data. And from these associations, we make an inference. We infer, because we can't see them, something about the processes which have ultimately produced the data we're observing. So we don't actually see this link unless we have some control via simulation, etc. What we normally have is these. We have spatial data. We want to know something about these, and we can directly measure these. Okay, so we have to make an inference on something we can't see. Now, in the visible realm, this is the kind of thing we can see, our data. There are various, what makes these things special in the spatial realm is that there are issues around these data, things like spatial dependency, for example, and the modifiable error unit problem, which makes these associations dependent upon the scale at which we're measuring our data. These are issues which are visible to us. They're data issues, essentially. There are other issues down here which are invisible to us, which again makes these things special in the spatial realm, in that they're process issues. They're things about processes, and this is the topic of today's talk. It's possible that these processes actually vary over space. So we may not have exactly the same set of spatial processes operating everywhere. That's a possibility, which we should allow for. So this is a concept, this leads us into the concept of local models, which have been around now for a long time. Not just geographic weighted regression models, there's a whole set of Bayesian spatially varying coefficients models and other types of local models around which exist in different areas. They all try and do the same thing. They perform a local version of what are traditional global models. And they deal with process non-stationarity. So the idea is we have some kind of relationship in a global model. Let's say this thing here, with y is a function of x, just a single covariate. In a global model, we're assuming that this parameter here, beta 1, is the same everywhere. Okay, so this is our study area, whatever it is we're looking at. We assume in a global model that this is constant. It's just one color. In a local model, we say, well, okay, that might actually vary. Now, this is data. It's not something we observe. This is our measurement of process. It's how y is a function of x1, how y relates to changes in x, this x covariate. So, and how y responds to changes in x might vary over the study area. And that's what a local model allows. It allows this parameter to vary over space, whereas a global model doesn't. It's fixed. Now, to make this kind of distinction quite clear, I often use this analogy of climate in the United States. So suppose I was giving a lecture to you on the climate of the United States, and I said the average rainfall in the United States is 32.2 inches of rain per year. That's the image you would get. Suppose you were from outer space. You would say, well, okay, I'll have to assume everywhere has the same kind of rainfall. It's 32.2 inches. That's my one value I have. Clearly, that's an average. And as such, we know it's kind of meaningless. Oh, sorry. It's meaningless in terms of how it represents this space, because this is more like reality. We know that rainfall varies across the country quite dramatically. From Hawaii to Nevada, we get to big variations in average rainfall per year, annual rainfall. But we're not seeing that, okay, if we just represent the rainfall by an average. Well, that's exactly what we're doing here in terms of processes. The climate example is in terms of data, and you'd think I was being ridiculous by just talking about an average rainfall across the United States. Well, for 100 years, we have been talking about an average of processes. We've been calibrating global models where we get one value which is assumed of a process, which is assumed to apply equally everywhere. What local models do is allow the pattern behind the average to be seen. Okay. So the problem is in local models, suppose we want to calibrate a model which relates a variable y to a set of covariates x1, x2, xn in one location I. Now we have to have a sufficient number of data points in order to do that. Suppose we have 100 observations of y, x1, x2, and xn at this particular location I. Then that's fine. We can use those data to calibrate a model specific to location I. And we could calibrate the same model for another location, let's say another city somewhere or another country. Right? And if we've got lots of locations and enough data at each location, that's exactly what we would do. Okay? There's no problem in doing that. The problem comes in the fact that we don't often have multiple observations at each location. Typically, we have just one observation of y, x1, x2, x3, xn at each location, and we have that for a set of locations. So we can't just calibrate a model for each location based upon one set of data. It's just not going to work. So the solution to this in local modeling is to borrow data from nearby areas, but not just borrow the data and give them all the same weight. Weight the data according from 0 to 1, according to how far the data are from the regression point. So if there's where I want to calibrate my model, I want to know what the processes are like at this location. Well, I don't have enough data there. I'm going to borrow data from nearby locations, and I'm going to weight those data according to how far away they are from the regression point. The further away they are, the less weight they're going to get in my regression for this location. And I can do this then for any location in space. I can just borrow data and apply the same kind of rules. The weights are all going to change because I've changed my regression focus. But I will then have enough data at each location to calibrate a local model. Now, the problem in doing this is, well, what kind of weighting scheme are you going to use for this? And this is called the bandwidth in local modeling. And it's a very important parameter. It's a trade-off between bias and variance. If we have a very large bandwidth like this, then we clearly have low variance. We'll have a lot of data, so there'll be the standard errors of our local parameter estimates will be lower, but we'll have a high bias, meaning we'll have a bias in the parameter estimates representing this location because we're using data from farther away, and we're assuming, I think quite reasonably, that if the processes are varying, they're not just varying randomly, they're varying with some spatial dependency. So further away data are more likely to be the result of different processes operating here than our nearby data. The processes are more likely to be similar here to this focal point than they are from out here. So that's why I would get more bias for the results in this location if we borrow data from further away. Well, the solution then is, let's have a small bandwidth. Well, if we have a small bandwidth, yeah, we'll get low bias, that's good, because we're only taking data locally, but we might have a high variance. The standard errors of our local parameter estimates might be very high because they're based on very few data points. So we have to find, in local modeling, we have to find an optimal bandwidth, which is a selection procedure. And it's found by optimizing a goodness of fit criterion, such as Ake-Ike information criterion, which trades off bias and variance. And for AIC, the smaller the value, the better. So basically, we try a whole lot of bandwidth in the calibration of these models, and we find out which one gives us an optimal score of our goodness of fit criterion, this thing that measures bias and variance. And there's a whole paper on this in how we measure bias and variance accurately in spatial statistics fairly recently. Okay, so we can get a bandwidth out of local models, and this bandwidth is closely related to how the processes operate over space. So in a model, we can have a mixed set of processes, some of which might be very local, that is, over very short distances. So the map might look like this. Some model assumes variation in them, either like this, a kind of regional variation, or a very localized variation. And whenever it way these parameters are distributed, or processes are distributed, we can measure these within local models. So for example, in multiscale geographic weighted regression, we get a separate bandwidth, an optimized bandwidth for each of our covariates. And so some of these covariates, the relationship, the conditional relationship with Y might vary very locally. Some conditional relationships might vary regionally, and some might not vary at all. It might be global. In fact, all of them might be global, in which case the default is we just get a global model. We don't lose anything. And this model type is described in a 2017 paper in the Annals. Okay, let's get back to the topic in hand, the presidential election. Okay, so this is what happened in 2016. And we all know the consequences of this, that although Hillary Clinton won the popular vote by about 2 million, Donald Trump won the election via the Electoral College distribution of votes. So what we want to know is, what are the factors that associate with voting for the Republican Party, and what are the factors which associate with voting for the Democratic Party? Well, there's about 8 months of work in this one slide, because this is in modeling, I think in empirical modeling, this is one of the hardest things to do, is variable selection. And so this is basically based on the literature, hypotheses, trial and error, talking to lots of people about these things. But we came up with 14 socioeconomic variables, which we think relate to voter preferences: age variables, gender, race, foreign-born, people with health insurance, income, education, income distribution within a county. These are county-level data I'm working with. Manufacturing employment, turnout, third-party voting, and population density, which separates kind of urban and rural areas. So we have 14 covariates in this model, and all the variables, including the Y variable, are standardized. They're all got a mean of 0 and a standard deviation of 1. Now, I'm just going to calibrate a global model to begin with these variables, just to see what happens as a kind of baseline. So my variable of interest is the percentage of people who voted for the Democratic Party in each county. And this is in a straight fight between Democrats and Republicans. And here are my covariates, the 14 covariates I mentioned before, and the parameters of interest to these betas. So here are the results, the global results from the 2016 election. The model is explaining about 66% of the variation in Democratic percentages over the counties. And I'm just going to color code these. The ones I haven't color coded aren't significantly different from 0, so I'm not going to talk much about them. All the variables are standardized, so we can actually use these values to compare the kind of strength of the associations we have. The ones color-coded blue, the stars, by the way, are at the 99% level of confidence. So the ones in blue are ones which associate positively with the Democratic vote. The ones in red are those which associate negatively with the Democratic vote. So in counties with a high proportion of black voters, Hispanic voters, a high proportion of people who are educated to at least bachelor's level, all of those have a strong influence, positive influence on the Democratic vote in those counties. As income increase, median income increases within a county, that has a negative impact on the Democratic vote. And then these ones have a lesser impact, you can see by the magnitude of these, but they're all have an influence. So population density, which is again, counties which have a high proportion of urban population tend to vote Democrat. Interestingly, where there's an increased vote for the third party candidate, and obviously a third party candidate varies across the country, it tends to favor the Democratic Party nationally. As turnout increases, that tends to assist the Democratic vote. Percentage of foreign-born people, as that increases, that tends to impact positively on the Democratic vote. And the percentage of people with insurance, health insurance, as that increases, it tends to impact positively on the Democratic vote. So this is the kind of standard result you get from a global model. And just to show you that this isn't a kind of a fluke of just the 2016 election, here are the same model calibrated for the 2008 and 2012 elections. And you see pretty much the same kind of story in all three elections. If you look at the lines here again, the color-coded, the 3-star bar now is actually a pretty stringent, significant level. It's 1 in 1,000 false positives here. So they're quite strong relationships, these. But you can compare the magnitude of these parameters through time. So the percentage African American population in each county obviously has a very strong influence on the Democratic vote, has done in all three elections, but it's actually increased. It's gone up from 0.36 up to 0.53, represented by this kind of trend. The percentage Hispanic population, again, has a strong influence on the Democratic vote, but it's remained relatively stable through time. Obviously, the Trump election galvanized the black vote in here, but not so much the Hispanic vote. Education, look at the difference between 2008, 2012, and what happened in 2016. It polarized the country based on education. Most people with a bachelor's education tended to vote Democrat, and those without a bachelor's education tended to vote Republican. And that was a big change in this election. Income, the influence of income has actually declined. And well, it was about the same for 2008, 2012, very strong influence. It decreased in 2016. Why? Well, Trump appealed to low-income voters. He got them to turn out and vote for him. So as an influence on the Democratic Party, this is a Democratic vote, that's why it's gone up here. It sort of lessened the impact on the division between Republican and Democrat votes because Trump suddenly appeals to low-income voters, and then so the income effect was much less in 2016 than it was in previous elections. Not much happened down here. These variables really not much, nothing going on. Look at the magnitude of the parameters. Then we've got these consistent results down here. Population density. The urban-rural divide is weakened in the 2016 election. The third-party vote is up and down because of the different third-party candidates. That's nothing we can say anything about systematically. Turnout is an interesting one. It was quite a high influence on the Democratic vote, positive influence, and it became much less. It halved in 2016. Why? Well, Trump got elected because he got his voters to turn out. That's his strategy. He goes for increasing turnout. He's not trying to capture some kind of the middle ground. I don't think the middle ground exists anymore. There are very few people in it. His strategy is to get his supporters to turn out, which is what he did very successfully in 2016, allied to a kind of not very enthusiastic Democratic support for Hillary Clinton. Percentage foreign-born has remained pretty much constant, and percentage insured has gone down a bit. Okay? So I mean, basically, it's telling us the same story, but 2016 was an interesting election. Some things did change in influence. Now, there's actually a problem with most of what I've just said, because if we look at the residuals from the ordinary least squares, the global model, they look like this. Okay, so these are the percentage errors in our predictions. Not only are some of them quite high, we've got -50 to about +50 in some areas, the extremes, but that's not a random pattern. Okay, it's obviously very clustered. We've got the reds together, which are the over predictions, and we've got the blues kind of together, which are the under predictions. So that invalidates most of the inference from much of the inference that are made from our global statements. Okay, so the estimation is poor. We've got quite large. Some residuals are quite large, but they're also spatially clustered. Okay, the Rand's eye is actually 0.3. It makes inference problematic, and it's an indication of spatially non-stationary relationships. So the solution is calibrate this by MGWR. You can download the software for this. Here's the website. You can download it in various formats, and there's also a manual, and there's also some sample data sets. And there's a GUI attached to this. It's very easy to use. Well, the program behind it is actually very complicated. Now, when we calibrate, there's the OLS residual map. When we calibrate this by MGWR, you see the difference. The R-squared shoots up to 0.95. Most of the residuals are in this -3 to 3 bracket, very small. Our model is actually very accurate. And it's not, there's no dependency in the residuals. The Moran's-I is 0. Okay, and we get a very good, very accurate fit. There's a predicted percentage of Democratic vote. There's the actual percentage. And along with our MG2I calibration, we get these bandwidths, these optimized bandwidths for each of the covariates. Now, this is the number of nearest neighbors it's borrowing data from. So when you see the number being very large, and these are the confidence intervals on these bandwidth estimates, it means you've got essentially a global relationship. I think in this study there are 2,815 counties. We didn't include counties with very small populations, and we haven't included Alaska and Hawaii. Okay, so these are clearly global relationships. What it means is the model, the relationships between democratic vote and percentage manufacturing and income aren't varying over space. Then we've got some, and the banding here is arbitrary. We've got some which are, the relationships are varying, but kind of slowly over space, the kind of regional variations. And we've got ones down here where the relationships between the democratic vote and these variables are actually varying very locally. So let me just show you an example of this. So the parameter estimates, the local parameter estimates we get. So now we're not getting one parameter estimate for each of these relationships, like that example I showed you right at the beginning. We're getting a map of the local parameter estimates. Yeah, and there's information on measuring the bandwidth uncertainty in this paper, again, in the Annals in 2019, I think. No, yeah, 2020, sorry. Right, so some relationships are actually global. This one with income is global. It's the same everywhere. These are the local parameter estimates. They're all the same magnitude. They're all between 0 and -0.4. So as income rises, proportion of people voting for the Democratic Party falls. And that's uniform across the country. The global estimate was -0.3. And the bandwidth is very, very large. Okay, so this is a global process. It's the same everywhere. The conditioned relationship. Some relationships do vary over space, kind of regionally. So this is the impact of Hispanic population on voting. It's obviously positive everywhere, significantly positive everywhere. These are significant local parameter estimates, accounting for multiple hypothesis testing. But you see a kind of regional division here, that in the Southwest, the impact, the effect of the Hispanic population is actually greater than in the rest of the country. And here's one where you get two separate effects. This is the Gini coefficient. So it's income disparity within a county. Most of the country, it's not significant. And look how it picks out the South. Right? There's nothing in the model that has the South in it. There's no indicator variables or anything like that. It's just telling us where this relationship is significantly negative. So in these counties, as income disparities increase, that tends to be associated in a conditional way with a high percentage for the Republican Party, a low percentage for the Democratic Party. Whereas out west, where you've got higher values of income disparity within counties, that's associated with a higher vote for the Democratic, a greater percentage vote for the Democratic Party. So you get these two very different kind of relationships here in different parts of the country, where in most of the country there is no significant relationship. Now that's all being hidden, of course, in the single global parameter estimate, which is, I think, insignificant. Then you get some relationships which are very local. There's the third-party vote. So this is the percentage of people who voted for a third-party candidate. And the impact here, again, is different across the country because there are different third-party candidates in different parts of the country. In most of the South and in the Central Belt, the Plains states, then the impact is significantly positive for the Democratic Party. So third-party voters are being drawn from the traditional Republican voters, and it's increasing the Democratic share of the vote. This would be mainly Libertarian candidate, I'm guessing. Johnson, I think it was in the 2016 election. Out here, centered on Utah, was an interesting third-party candidate who was Evan McMullen. And what you see here is, although he was very much on the sort of right-wing part of the spectrum, the local parameter estimates here are significantly negative. So he was actually drawing votes away from the Democratic Party. Now, why was that? Well, it's definitely an indication of strategic voting. There was a chance, I think, that people thought that Evan McMullin could actually beat Trump in Utah and take his electoral votes away from him. So you got a lot of Democrats voting for Evan McMullin, knowing that Hillary Clinton wasn't going to win in this state. Interestingly, the combined votes, I think, for Hillary Clinton and Evan McMullin actually exceeded that of Trump. So if there hadn't been total strategic voting, he wouldn't have had the Utah Electoral College votes. But again, it points out the importance of local modeling here, because we have different processes going on over space. And then this is the influence of the African-American population, which is significantly negative for most counties across the country, but of varying degrees. It goes from something quite small up to something very large. The impact varies. You might not be able to see it on the screen, but there's a lot of dark blues hidden away, the very darkest blues, which are actually over 1. Remember, these are standardized variables, so this is a very strong impact of the black population, African-American population. It's not, the variable's not significant in certain parts of the country, and these are all, it should be jumping out at you, all have a commonality, which is a very low proportion of African-Americans. So, Arizona, Colorado, Washington, Oregon, the upper Midwest states, Wisconsin, and then New England. Oh, and also South Texas as well, where there's a very high Hispanic population. Now, coming on to one of the important points of the talk is that we also get a local intercept in MGWR. And the interpretation of the local intercept is interesting because we've standardized all the variables. So we define the local intercept is the level of Y, in this case, the percentage Democratic vote, that can be expected if all locations have the same average data on the covariates. So in this case, if all the counties had exactly the same socio-demographic composition, how would the vote take? What would happen with the vote? So the local intercept tells us that, and it indicates if there's some kind of contextual influence on Y. That is a locational influence. I'll come back to that in a minute. Here's the map of the local intercept terms. So this tells us where we have, holding everything else constant, right? All the other covariates constant. Suppose we had the same average population in all the country. Remember, the average would be 0. All the covariates would be 0. So the intercept tells us what would happen if a county had the average demographic composition of the United States in it. How would people vote? Well, they wouldn't all vote in the same way. So the counties up here voted blue would vote for the Democratic Party. There's a significant intercept here, positive influence intercept here for the Democratic Party. It's saying that there's an intrinsic level of association with the Democratic Party in these areas, these counties in these areas, all blue. Where we have the reds, these are significant negative intercepts. These are where there's an intrinsic alliance with the Republican Party. Now again, nothing has gone into this map that like an indicator variable. This is all coming out from the data. All the white counties are those where there is no significant leaning towards, intrinsic leaning towards either the Democratic Party or the Republican Party. Okay? And it includes many of the sort of swing kind of states, including Arizona, and you see Florida. Look at the detail on this. I was at the University of Florida for 4 years, so I'm well aware of this kind of difference between northern Florida and the Panhandle and central and southern Florida. Certainly northern Florida and the Panhandle associate very much more like the Deep South. And you see that map, that coming out from the map very, very clearly. They associate intrinsically with the Republican Party, whereas the rest of the state is neutral. And that's why it's a battleground state. You see the influence in Arizona in 2016 is becoming a neutral state. Now, just in case, again, this kind of meshes, I think, with most of our perceptions of how the country allies itself politically, okay? So we've got a sort of liberal West Coast, we've got a sort of Scandinavian influenced group of voters up here in Wisconsin and Minnesota, We've got Liberal New England and Upper Michigan, and that kind of meshes with our feeling about the country. And then we've got the Deep South, which is a kind of Republican hotbed. So we've got the blue wall up here and in the West Coast, and we've got the Republican red wall all through the South. Now, just in case you think that's an artifact of the 2016 elections, we did the same model, calibrated the same model for 2008 and 2012. And here are the 3 maps of the local intercepts. It's not an artifact of the data. It's very stable over time. And you see some interesting kind of differences. You see the Florida kind of effect in all 3 cases. You see the same pattern of these, although we lost California from its intrinsic Democrat leaning in 2012 in the second Obama election, when I think there was a bit of disillusionment with Obama. If you look at Arizona, it's interesting because the red, which is a kind of intrinsic republicanism, starts to shrink over time. And next week it might well turn blue. We'll see. So you can see a lot of detail. In 2012, Utah became intrinsically Republican. Why? Well, the Republican candidate was Mitt Romney from Utah. So that meshes with that. And you see some incredibly fine divisions across the country in this kind of map. So this, I would argue, is telling us something about context. What do we mean by context? Well, we use this word to describe the impact of a person's location in space on how they behave in that space. It's really a shorthand term for what are probably largely unmeasurable effects of one's location. That these impacts, which are hard to define, but are probably there. Where we grew up and etc. has an influence on our preferences and on our actions. So there's always identifiable and measurable aspects of location, which we put into our model, and we've got to put those in. But there's probably aspects which we can't ever try to measure. They're ill-defined, and these come under this kind of label of context. So the kind of things that might be included within context are things like traditions or customs or lifestyles or daily practices, which are common to an area that affects social norms. So in some areas it might seem socially acceptable to do something, but in another area it might not be seen as socially acceptable. You've got the influence of family and friends, this kind of social imitation, who you talk to, either in your family or at work, etc. It might influence how you feel. The local media, there's definitely geographically targeted social media as well. The Brexit vote demonstrated that very clearly, and probably the 2016 presidential election was a result. The result was very much caused by targeted media in certain areas. So obviously there's selective news representation. I mean, nationally, you just have to look at how Fox and CNN, for example, report the same news. But that translates down to local news coverage, I think. And then there are differences in basic psychological profiles across space. For example, the feeling about private deprivation for the public good. That varies, I think, geographically, and there's actually an increasing amount of work in psychology which is demonstrating this. And I won't bother reading these out, but there's lots of interest in this concept about context within all kinds of behaviors. But most people agree that it's a very important effect. So, for example, Ryan Enos in his 2017 book, nobody doubts that context can affect behavior, and careful studies of neighborhood effect have strongly suggested it can. But the problem is, nobody knows how to measure it. So people say, how do you disentangle the effect of this context thing you're talking about, this kind of vague idea, from all the other socioeconomic effects that affect behavior? John O'Loughlin, in his review of 35 years as editor of Political Geography, or Political Geography, the journal, sorry. If context has remained a mantra in political geography, which it has, how do we measure its importance? That's a sort of rallying cry. And Ryan Enos said, however, the exact nature of contextual effects, how much they really matter, is elusive to researchers. Well, we have this solution now in local modeling, because if you look at our local model, which is this thing here, we've got y as a function of x with these localized parameter estimates. There's the intercept, and there's the slope parameters. Y and X, in this case, represent standardized variables. They've got a mean of 0 and a variance of 1. If we make that explicit, there's a standardization. It's just yi minus the mean divided by its standard deviation. And then we've done the same thing with the x's. If you rearrange this, it actually relates y, our observed value, the thing we're interested in, to 3 components. A mean, baseline, in this case, an average vote by county for the Democratic Party, an increment due to geography, geographical context, which is this local intercept term, and then an increment which is due to the external covariates in our model, the socioeconomic effects, the composition of our counties. So basically, the resulting vote has 3 components. It has a baseline, which I think was about 33% across the country as a mean, because many of the Democratic counties are very heavily populated. It's not weighted by population. Then we've got an addition percentage. We add to that or subtract from it an influence which is based upon socioeconomic characteristics of each county, who lives there, what type of people live there. And that's the kind of voting. These are percentage votes which would be added to that baseline or subtracted. So in these red counties, you'd be subtracting votes for the Democratic Party because of who lives there. In the blue areas, you'd be adding to the Democratic baseline vote, again, because of who lives there. And then that's the influence on the Democratic vote due to geography, due to context. And again, these are the percentages. So in the red areas here, we'll be subtracting up to 21% of the vote due to context. And in some of the dark blue areas, we'll be adding up to 14% due to context to the Democratic vote. This is just the intrinsic nature of people living in these areas. And when you add those 3 together, you get this map. This is a predicted proportion of Democratic votes by county. And there's the actual map. Those 2 are very, very similar. Now, given the dissection of the model, we can consider 2 scenarios. What would happen if every county had the same mix of population? And what would happen if geographical context didn't exist? How important is it? Well, scenario 1, what would happen if every county in the country had the same mix of population, had the same demographic composition? Well, there's our model with our 3 components. If every county had the average mix of population, that term disappears, it's 0. Yeah, and that's the resulting vote by county. These are the percentage votes. This is how we would vote in terms of just by geographical line, just by context. Okay, and it's a close call. It's difficult to know how this would translate through the electoral college into who would actually win this one. Scenario 2, what would happen if geographical context did not influence voting? So if geographical context wasn't there, well, we get rid of that. And what do we predict? Well, this is how we would have voted without geographical context. And there's no doubt in this case that the Democrats would have won this election. Okay, they would have taken all these kind of heavily populated blue counties and most of the South. It's almost the reverse of how we did actually vote, because that's how we did vote, okay, with a Trump victory. So if anybody tells you that geography doesn't matter, then you can point to these 2 maps and say that it does. And then just to finish, apart from determining US international relations, domestic policy, and the fate of the world, etc., for the next 4 to 8 years, are there any other implications from these findings? Well, yeah, there are 5 other ones. Transferability. This is a big issue at the moment. Our models don't transfer. Okay, we calibrate a model in one location, we calibrate a model in another location, and we get different parameters. Okay, what's happening? Okay, and this seems to be a problem, but it isn't a problem if we say that context affects spatial behavior, because we wouldn't expect our models to translate over space because of different contextual effects. So it definitely relates to the current debates on reproducibility and replicability. It has implications for the modifiable unit problem. The MORP, as it's called, is that the problem is that the conclusions we draw from any kind of spatial analysis of aggregated data depend on the definition of the spatial units to which the data are aggregated. And if we change the definition of the units, we can often come up with very different kind of results from our model calibrations. Now, if there were no spatial heterogeneity of processes, no non-stationarity, if they were totally stationary, would this modifiable error unit issue be a problem? Well, possibly not, because different aggregations of spatial units mixes different processes. And if the processes were the same everywhere, then there wouldn't be a problem. So one can argue that the MORP, the problem of modifying error units, is actually a result of spatially non-stationary processes. It has an impact on scale, and which is the topic of this seminar series. Through local models, and particularly through MGWR, we now have the means to measure the spatial scale over which different processes operate. Geographers have long talked about different processes operating at different scales, right? We say this all the time. Some things operate on a global scale, some things operate on a local scale, but we've never really been able to measure that. Now we can measure it through the bandwidth. I think very importantly, this topic is a bridge between two disparate views of our discipline. One is the space view, one is the place view, of nomothetic versus idiographic. This distinction has been with us since beginning of geography, possibly. In one view, we see space as a container. It's just somewhere to describe where things happen, okay? In another view, place is important. It's a feature of our lives that affects what we do. Local models, such as the one I've been talking about, provide a bridge between these two opposing views. Okay? We recognize context, the importance of locality, but we can quantify that. And then finally, I think we now have the beginnings of a new geography. I mentioned at the beginning, I think this is part of my first slide, the goal of research is typically to uncover something new about why things are the way they are. And as I said, we're often prompted to ask this question by observing data, and I emphasize the word data about things. It's a map of something, right? The map of something we've measured. And we notice that the data vary over time or space or both, like the percentage of people voting for the Democratic Party. But now we have a new geography. It's a geography of processes. And that's basically, we're looking at now maps which depict the local parameter estimates, which depict processes, not data. And then we're prompted to ask different types of questions, just as I was asking about those maps I showed you of the local parameter estimates from the model of the Democratic vote by county. Okay, so I'll leave it there. I've slightly over on my time by 5 minutes, and I thank you for your attention, those of you who are still listening. Okay.
Thank you, Stuart. I think we've got some questions. We definitely have some time. It's a little bit weird not to be able to have applause and whatnot, but we do have some questions. So I think that that will help facilitate some discussion and get some feedback.
Okay.
I think I have first up, we have some in the chat and some in the Q&A box. So I'll go through the chat and then to the Q&A box. Chris Justice said, very nice presentation and quite timely. His question is that given that only around 55% of eligible Americans vote using census data and your explanatory analysis, can you emphasize how would a considerably higher voter turnout change the election outcomes?
Yeah, so basically, do I have a crystal ball? I think this is actually a very good point, because we will see a high voter turnout. That's definitely the case. And it's impossible to predict the impact of that, because you don't know whether, in the 2016 election, Trump was very successful in getting his voters to turn out. And no doubt he will do the same again in the 2020 election. The question is, can Biden and the Democratic National Party get